Welcome everyone back to the calculus videos. I am your host, Dr. Williams. Sorry, I just can't, it's just this microphone. It's really fun to talk like that. Also, this is like the third take I had to do saying that intro because I could not get my voice to stop cracking saying the word videos in that type of voice. So, anyway, in this video, what we're going to be doing is going over some example problems of the disk method using both dx and dy. Now, we know we're using the disk method in this one. So you don't have to go through and answer that first question that I posed in the last or in the end of the last video. But still, for practice, it's good to recognize that in every single one of these examples, what makes us use the disk method is that the area in which we're rotating is in constant contact with our axis of rotation. So why don't you take a look at this problem right here and see if you can solve this one on your own. And also, we could go through and solve all of these integrals that we're finding, but I think the better practice is just how to formulate the integral itself. And you guys know how to solve them either using methods of integration or using f and I and t on your calculator. So I'm not really going to concentrate on that. We're just looking to get the integral that represents what this volume is, and we're going to consider that a solution to the problem. So go ahead and give this one a shot. Okay, so if you tried this one, maybe some of you decided to graph this region, maybe not. But if you do, what you'll see is that square root of x looks something like this. This is 4. So the region that we're looking at is this shaded region right in here where we have y is square root of x. And if we rotate that thing, let's see if I can do this, we'll get a solid that looks kind of like that. Maybe it's somewhat like a bowl shape, but really this bowl would be filled in, so that'd be a pretty pointless bowl. More like a giant paperweight or something, I don't know. So anyway, again, our area is in constant contact with our axis of rotation. The problem indicated that we are rotating this thing about the x-axis. So if we draw it, it looks something like this. So if we wanted this, our radius function, remember, the radius of each cross-section is this right here, which is just given by this function. And again, if we took a slice and looked at an individual cross-section, it would be a circle with that radius that I highlighted right there. So therefore, if we want to find this volume, this would be the integral from 0 to 4 of pi times our radius squared, which our radius is square root of x. And there we go, that's it. This is all we're going to do for the solutions to these, just coming up with the integral. Now, recall you guys can solve these integrals, okay? But that's not what we're trying to practice here. We're trying to practice how we actually just formulate the integral in and of itself. Okay, so let's go on to another one. Okay, so again, read this problem, give it a shot. Recall what we did on the last problem. I drew a picture. Drawing a picture is always really, really helpful to do, at least for me. It always helps me visualize what's going on, so hopefully it can help you too. Okay, so if we've looked at this one, well, again, we got the function square root of x, which looks like that. It's bounded by this line, x equals 4, and also the line y equals 1. And it also says we are rotating about the line y equals 1. Okay, so again, let's look back. We're rotating about this line y equals 1. The region which we're looking at is constantly in contact with that axis of rotation, so we're going to use a disk method. If we go to do this one, it's going to look very similar to the shape we had before. Again, like oops, it'll go down here, not like that, sorry. Yeah, just kind of like this like bowl-looking shape sort of thing. But anyway, this one's just going to have a slightly different shape. So in this case, what we got to find is we got to find what that radius is. Okay. Well, we know that this function, the curve right here, is y equals square root of x, and this line is y equals 1. So if we want to find that distance, well, if we take square root of x, which I'll draw that in blue, square root of x will be the blue line. But we don't want the blue line, we want the red line. So what do we have to subtract from it? We have to subtract from it 1, and that's y equals 1, not y less than 1. That kind of looked like a less than sign when I was drawing that. So anyway, if we want to get that red region in there, that's just going to be given by square root of x minus 1. All right, so now we have our radius function. That's the radius of our cross section. So all we got to do is just write the integral for this thing. Now, what's different about this one as opposed to the last one? The last one started at x equals 0. This one has to start at this point right here because that's where the solid starts. So we want to look at where square root of x is going to be equal to 1. Well, that's simple. That's just x is equal to 1. So now we got the limits of integration, 1 to 4. We have our radius function, which is this right there. We know we're using a disk method. The last thing I didn't talk about is that we're rotating about the line y equals 1. That is a line parallel to the x-axis, so we know if that's the case, we're going to be using dx and not dy. So therefore, this volume would be the integral from 1 to 4 of pi times our radius function, which is square root of x minus 1 squared dx. And again, we could go through, we could distribute that square, or we could use f and I and t on our calculator to do it. But like I said, those things are kind of secondary compared to just setting up the integral. This, if you can get to this step, this is really where I want you guys to be with watching these videos, and we can worry about the rest later. All right, so let's get crazy here. Okay, so now let's do this one. Take a little bit of time to do this one because it's a little bit different. Remember, go back to those rules I told you to write down at the end of the last video. They may help you out with this one. Okay, so if you've given this one a try, well, one thing you might notice is if you graph 2 over x, it looks something like this. So that's y is 2 over x. And it says it's bounded between the lines y equals 4 and y equals 1. So y equals 4 is right there. Every time I write that, it looks like a less than sign. Something's being funky with the smartboard here. And this is the line y is equal to 1. So the region we're talking about is this one, because again, remember it says it's bounded between this curve, the y-axis, and then these two lines. So that's that region we're talking about here. Now it says we're rotating it about the y-axis. So our axis of rotation is going to be like this. And so notice the axis of rotation is not only parallel to the y-axis, it is the y-axis. So that should clue you in on the fact that we're going to have to use dy to evaluate this integral. Because if we're evaluating it that way, our radius is now this distance. It's that horizontal distance, okay? So one thing we're going to want to do is kind of rewrite this function, and we want it to write it as x as a function of y. So if we do that, we'll get x is equal to 2 over y. And that's exactly what our radius is going to be. So we got our radius function, we got our limits of integration from 4 to 1, so we should be good to go. So if we write this volume, the volume will be the integral from 1 to 4 of pi times 2 over y squared dy. And there we go. We got that's the volume, or that's the integral expression that's going to give us the volume of that region. So what's different about this one as opposed to the last ones? This is the first case where you've seen how we have to use dy. Now, if, for example, this region was instead rotated about the line y equals 1, maybe, if it was rotated this way, then in that case, we would have to use dx. We would still be using a washer method because we're in constant contact with our axis of rotation, but we would be using dx in that case and not dy. All right, so let's look at one more. Okay, let's look at this one. Remember, what you want to do, draw the picture first. Determine, even though we're using disk method, still just make sure you can see that this region is in constant contact with the axis of rotation, and then determine, based on our axis of rotation, if we're going to have to use dx or dy. Let's give it a shot. Okay, so if you tried this one, let me scroll down a little bit. So we want to look at the graph y equals square root of x minus 1. Let me go up a little bit more. Okay, so if we draw that, that will look like this. This is y square root of x minus 1. And then we have the line x equals 3 right here. This value would be 1. And we want to actually and oh, I'm sorry, and we're bounded by the x-axis. So the region in question we're talking about is right here, and we're going to be rotating that about this line. So keep in mind the region is in constant contact with the axis of rotation, so it's a disk method, but we're also rotating about a line parallel to the y-axis, so again, we're going to want to use dy. So if we want to find this, our radius function is going to be this distance right here. Well, how do we find that distance? Okay, again, I'll use blue. We're going to find that distance where if we take this whole distance, which is equal to 3, and subtract this distance, then we'll end up getting our red distance. So what we got to do is find out how do we get this blue distance. Well, the answer is we got to convert this function right here from y as a function of x to x as a function of y. So if we have y is square root of x minus 1, this gives us y squared plus 1 is equal to x, and that's going to be what that distance is right there. That distance will be that exact same function, y squared plus 1. So if we want to find that red line right there, that's going to be, you know, our radius function in terms of y, which in this maybe you guys didn't hear that voice crack and I just made it completely obvious, but it was kind of a bad one. At least it sounded like that from this end. So this whole thing would end up being 3 minus y squared plus 1, which would just give us 2 minus y squared. So we got our radius function. Now in terms of limits of integration, we know we're starting at y equals 0, but we got to find what this value is right here. So we can find that just by plugging x equals 3 into this function right here, and that will give us square root of 2. So if we go to evaluate this guy, the end integral should look something like this. The volume is going to be the integral from 0 to square root of 2. Remember, we found that this was y equals square root of 2 right here. And then it's going to be pi times our radius, or our y function, which is this, 2 minus y squared. And we want to square that, and then do dy because we're using y's, and there we go. That's the expression that's going to give us the area of the solid generated. Now that solid, what would that look like? That one would look a little bit more like a dome shape or something like that. You can imagine if we just took this shape and kind of revolved it. This isn't going to be to scale at all, but it would come up and it would be kind of like a dome sort of thing like that. Okay, so hopefully these examples were helpful to you. In the next video, we'll look at examples of how we do the washer method.